All right, so today we're going to try to wrap up the electrical energy notes. So I'm going to try to get through your entire packet of notes that you have in front of you. Notice that the top of these notes are more of like a chart. That's not how it's going to be set up on the video, so just make sure that you pay attention to what things need to go in the chart and that you're in as I flip the screens. Remember that you can always pause and go back on the so we're going to be looking at three different measurements today, and that's going to be electrical current, voltage, and resistance. So as you will see, these notes are going to be about electrical current, and that means a continuous flow of electric charges through a material. So again, electric current, the description would be that it's a continuous flow of electric charges through a material. And we measure this in amperes, or amps is the abbreviation. And some other little facts that you might need to include or know about is that the higher the electrical current in a wire, the more charges are flowing through it. So what does that really mean? So you have a wire and you have a complete circuit like shown on the diagram here. We have a power source, we have a wire, we have a bulb, and then we have a switch. And so we have, if we have an electrical current flowing, that means that electrons are flowing through the wire to the bulb and back around to the battery source. And if there's a stronger current, that just means that more electrons are flowing past any given point at a certain time. Another way to think about this is a conveyor belt. And here it's showing tomatoes on a conveyor belt. Those tomatoes are somewhat confined on the conveyor belt. And so you have them moving a straight path, all going in the same direction. And you can speed up that conveyor belt or you can keep it slow. And that is just showing you that in one point along that conveyor belt, possibly where that man is standing, it's going slower, there are less tomatoes passing him every second. If it's going faster, there are going to be more tomatoes that pass him every second. And so that's just showing you a different way of thinking about electrical current. Moving on in your chart to the second row, you're going to just include this information about voltage. Again, this is a different type of measurement you can take with an electrical current. Voltage is a force that makes electricity flow. So it's got to have some power to it. Well, where do we get that power? We usually get it from a battery or a generator, but basically it's just the source of energy for the circuit that you're running, like the picture that we saw in the last slide. It is measured in volts, which is abbreviated with a capital V. All right, two types of materials, and we need to talk about these before we really talk about resistance. Now, make sure that you understand that on your notes, we're down here beneath the chart. Two types of materials that exist. If you take all the materials out there and you break them into two categories, insulator and conductor. And an insulator is also known as a resistor. A resistor basically resists the flow of electrons through it. So it can make it very difficult for electron charges to flow. Non-metals are examples of insulators, and some metalloids are also examples. Yesterday in the lab, we used a balloon. A balloon is made of rubber. Rubber is an insulator. So that balloon would not allow the electrons to keep flowing through it. The same with the piece of wood that we used. Now notice that over here on the conductor side, we also have the word metalloids again. So its conductors would be metals, but also metalloids. So I'm going to take you back in time where we studied the periodic table, and I'm just going to kind of put it into a rectangle format. When we studied the periodic table, we had the metals located on the left side. We had kind of like this staircase zigzag line, and those were the metalloids. And then over here, we had the non-metals. And so taking you back in time a little bit to when we talked about the periodic table, I just want to remind you that the metalloids along the staircase, they have properties of both metals and nonmetals. And of course, some of them are insulators, while others are conductors. So just wrapping this up, a conductor is something that allows those electric charges to flow very easily. So as far as a current, you would have much more electrons moving through a conductor than you would through an insulator, if at all, through an insulator. Examples of conductors are copper, aluminum, and gold. On this screen, what you're seeing is just kind of like the spectrum of how well things allow electric charges to flow through them. And you can see down here at the end, we've got rubber, not very good conductor, and we've got wood, and both of those were used in the lab yesterday. As we move closer, you can see that most of the ones listed by conductors are metals. And we're going to move on to start talking about the last part of your chart, which is resistance. This is the last type of measurement you need to understand for electricity, and it is the measurement of how difficult it is to push the charges along. So how difficult is that battery or that energy source to force the current to flow through the material? The reason why it would be difficult or why a material would have some resistance to it is friction. Friction, again, is the rubbing together of two materials or two substances. And when that happens, we get slowed down motion, but we also get heat energy output. So some of the kinetic energy of the rubbing particles is transferred into heat energy output. So as you know, insulators resist the flow of electrons. So in an insulator, there's a lot of friction between the electrons trying to move and the material. And it doesn't allow that to happen very well, if at all. And this sentence right here is really important, but we're going to kind of break it down and talk about it. So the greater the friction is with the material and the electrons, the greater the resistance, not allowing those electrons to travel. Well, if the electrons are not traveling through the material, then you have less of an electrical current, which we studied in the first screen of these notes, which is just how many electrons are passing by a certain point within a second. And if you don't have many electrons passing through a certain point, then you have some wasted energy because you have a power source that has energy and it is willing to send these electrons through. However, they're not going through, and due to friction, it's putting out heat. So how many of you have ever plugged in something and you feel a wire that's getting warm to the touch? Or if your computer starts to get warm, that is showing that there's some friction going on. And the heat coming from it would show an inefficient machine, just like heat coming from a wire or something that you're expecting electricity to flow through would show that there is some problematic thing happening. Now, speaking of wires and whether they allow electrons to flow easily or not, two things also affect the flow of electrons. If a wire is thinner, electrons will not flow through it as easily. And if a wire is longer, it will not flow as easily. So both of those create more resistance and allow less electrons to flow in a given time. Now, the measurement unit for resistance is ohm, okay? And we will be talking a little bit about Ohm's law as we get deeper into creating circuits. Speaking of circuits, we're moving down into your notes, so there's the bottom of your first page. An electric circuit is a complete, unbroken path through which electric charges can flow. So when we say complete, we mean it's making an entire circle, that everything is connected. But it also has to have certain things in the circuit. It has to have a power energy source. This is where we can determine like how much voltage it has. And it also has to have wires, and those would be made out of conductive material. Okay, so that's why they're also known as conductor leads, leading those electrons along a conductive material. And then lastly, you need a payload, or also a payload can be named a resistor. So it's kind of like an insulator, but what it's going to do is slow down the movement of electrons. A bulb is one example of that. So in this circuit right here, you have a power, you have a conductive material wire, and I'm going the opposite direction. I want to show you the switch first. And then you have a bulb, which would be considered a resistor. The electricity is going to flow through that, and then wire in that bulb, which slows it down. And then it comes, and you can, this is a switch. You don't necessarily have to have a switch. This is one thing that you don't have to necessarily have in your circuit, but it is often. What this is, if you lift this bar right here, that would open the circuit, and therefore electrons are not flowing anymore. But if you close it, it allows the electrons to keep flowing through the metal. All right, moving on. We're going to be drawing diagrams in the future, so I want you to be able, when you look at a diagram, to understand it, but also be able to use some of these in your drawing. So here in this one, you need to draw the symbols in right here and just understand how they're actually used in the diagram below. So a wire is just represented by a single line. A switch often just looks like something you would draw as a door. It has two circles on either side of where the switch is. And then you have a power source, and this would be possibly a battery right here. So notice how the longer side is considered the positive terminal, and then you have the negative terminal. So this would be your energy source right here. And now you have a resistor, so this could be like a light bulb where the energy is actually being used and transformed into light and some heat. So that is an example of the symbols and how you would draw a diagram. All right, types of circuits. There are two main types of circuits. And you're probably aware of this, but as far as your notes, you are on the back side, halfway down of the first page. So a series circuit. The main thing you need to know with a series circuit is there is only one path that the electrons can follow. All right, so here you can see the battery, and we learned on the last screen that the longer end is the positive and the shorter end is the negative. And while it is drawn differently on a lot of the diagrams you would see, the electrons flow from the negative side all the way around through bulb 1, bulb 2, bulb 3, and then back to the positive end of the battery. There is no other path that the electrons can follow. That's it. It's kind of like that conveyor belt. They're stuck on there. Now, a parallel is different because electrons that leave from the negative side and go, some of them can go this way, some of them go this way, some of them go this way, and then eventually they're all going to meet back up and come back around. But it does allow for different paths that the electron can flow through. Okay, and when there's a break in the wire, I'm going to go back. If you have some kind of circuit break or something that happens in the wire where the flow is cut off, then none of these resistors are going to work. So if these are bulbs, none of them light. However, there could be a break here in where you still would get one light bulb that would work because the current is flowing around and around on that light bulb. So that is one other difference between series and parallel. All right, so you try it. Is this considered a series or a parallel circuit? And why do you think that? Okay. I do have a link here to a BrainPop video. However, I don't know that it's going to work. You are welcome to try to link to it. All right, so as you can tell, we are not going to get through all of the notes that you have on your paper. So So we will finish these up when I come back on Monday, and we'll be talking about breaking a circuit and the two different